Hello. Oh, is that interesting? Yeah, it sounds good.
Hello. Welcome, everybody. Thank you all for coming out. Great attendance for our first colloquium of the fall term. It's our honor and pleasure to have our own Nick Scoville and Andreas Faisst giving our first colloquium of the new year, the new academic year. So I know you don't want to hear from me, so I'll give a very quick introduction, especially give our dual speakers. So Nick, of course, many of you here know better than I do, although I think I know him fairly well from almost my whole career. He's the Francis L. Mosley Professor of Astronomy Emeritus here, did his PhD and BA at Columbia with Phil Solomon, where he got into studying things like molecular clouds and star formation in the galaxy. And he's worked over his career on a tremendous range of multi-wavelength astronomy, from optical IR radio astronomy, trying to understand things like AGN, infrared galaxies, star formation in galaxies, cosmological evolution of galaxy populations. He was the leader of Cosmos, one of the largest HST large survey programs, pushing the boundaries at the time of what was considered high redshift, although, now Z-twiddle-1 is, very low redshift, I suppose, compared to some of the things we might hear about. He also served as the director of OVRO here for a decade in the 80s and 90s, and has been honored through his career with many awards and honors. Recently, a few years ago, the Henry Norris Russell Lectureship of the AAS, and has just had a tremendous influence. There's so many stories people here have of Nick's influence on their careers, and I'm one of many people where, as a junior astronomer, I got to know Nick. We were just saying through some Cosmos meetings, but he was always tremendously encouraging and excited about the science I was doing, and convinced me that this wasn't just a technically interesting job, but one you could really have fun doing while being really passionate about it. And our other speaker is Andreas Faisst. And don't worry, Andreas, we don't expect you to quite have built up the resume of Nick at this stage, but we also know well, is here at IPAC, an associate research scientist at IPAC and Caltech. Did his PhD at ETH Zurich in 2015 on the evolution of star forming and quiescent galaxies through cosmic time, then came to Caltech as a postdoc and has been here since. I think first at Caltech, on the Caltech side officially as a postdoc, and then moving to the IPAC side, becoming a research scientist there. He's worked again on similar topics: star formation, galaxy evolution, trying to understand sort of multi-wavelength properties of galaxies and synthesize that into our understanding of star formation, with instruments ranging from ALMA and Keck and JWST and many others to probe this across wavelengths and across time. So let's hand it over to Nick to start us off, and look forward to their talk.
Okay, now can't teach an old professor how's the sound? Is it loud enough? Some people raise their arms. Okay, so what I'd like to do is hark back a little bit to the way lectures used to be when I was a lot younger than I am now. And that is that I would like people to ask questions during the talk, and feel free to interrupt me. I'll try to keep an eye on Sri. I bought following in Teddy Roosevelt's footsteps. Speak softly and carry a big stick. The Sri pledged to harass me during this talk. Right, Sri? Okay, George can take care of Sri also. So I was playing a little movie in PowerPoint of nearby galaxies sampled with modern, mostly space telescopes. And it's really impressive how wonderful those images are. And I will refer to them during the talk occasionally. one thing I'm going to do is, it's not just evolution of gas and star and galaxies, which I'm going to describe, but there have been several problems with respect to local galaxies, understanding some of the things, and I'll explain the lack of understanding. And then, when you're retired, you get to sort of daydream about, how to solve problems that you never solved when you were being paid for it. So I hope you'll enjoy that part of it and learn something new. And the conclusions are actually very simple. So, don't be deluded because now let's see, how do we? Oh, God. This one? No, for changing slide. But I did. Good, we have a competent person here. So this first slide I'm showing is, of course, a view of the Milky Way taken on a dark night. I'm not sure who gets credit for the image, but it's covering roughly plus and minus 20 or 30 degrees of galactic longitude, centered on the galactic center. And you can see what a mess our galaxy is. We're sitting in the plane of the galaxy, and you see all the dust clouds along the line of sight obscuring the more distant objects. And the galactic center has roughly 20 magnitudes visual extinction. So it basically is not seen at all in the visible. You have to go into the near infrared to see it, where the extinction is 10 times less. But now, figuring out what's going on in our galaxy, and this is sort of harking back to early research, which I did. And where's the pointer? This one? Yeah, sure. Oh, actually, I can use the. No, but actually, I should, so that people online can see. Oh. So let me back up. What I need is somebody who's competent to run the slides.
Stay on this slide or go to the next one?
Yeah, let's go to the next one. Oh, we're sorry, let's go back. So if you look at the material, you look down on the disk of the Milky Way, this is a plot of how things vary with radius in our galaxy. And there are a bunch of different important species of gas, H1, molecular hydrogen, ionized hydrogen. Okay. And the Milky Way is actually very typical of nearby spiral galaxies. So, this serves as a good model of what is happening in nearby galaxies. It's only the Milky Way that you're looking at. So these are compact H2 regions, which are sampled in the radio portion of the spectrum without any extinction. Their distribution peaks at about 5 kiloparsecs radius from the galactic center. And then the atomic hydrogen is basically flat with radius outside the galactic center. And the rule of thumb, essentially all nearby galaxies, is that the atomic hydrogen gets up to about 10 to the 21 per square centimeter column density looking through the disk of the galaxy. And any excess gas, here's the H1 plot, and any excess gas above 10 to the 21 becomes molecular hydrogen. And so that's a very simple rule to base one's understanding on galaxies. The let's see. So here's the molecular hydrogen radius, and then there's a even higher peak in the molecular hydrogen density with some very massive clouds, which are greater than 10 to the 6 solar masses. Yeah. Oh, it's just these arrows. Okay, so there are several ways to probe the distribution of gas. One is looking at the dust obscuration. Obviously, that's indicative of where there's also gas. And then the IR emission from the dust, which the IR emission, of course, is radiation absorbed from young stars by the dust and then re-emitted at longer wavelengths. And I'll describe that in a second. And then CL rotational line. And the CL rotational line emission is what's been used for most nearby galaxies, determining the mass density of molecular gas. Yeah. So I wanted to show a spectrum of CO in the Orion molecular clouds. And this is the original discovery spectrum for CO done by Penzias, Wilson, and Jeffords back in the early 70s. And this is the CO line that they observed on the center of the Orion Nebula, M42. And the peak brightness is 40 degrees Kelvin. That represents basically the kinetic temperature of the gas, which is the molecular gas, which is in equilibrium in terms of exciting the CO. And then the particular thing that they note is that the line width is actually 6 kilometers per second. And for those, I think probably most of you in the audience aren't familiar with this fact, the speed of sound at, say, 40 degrees Kelvin, which is the kinetic temperature of the gas, the speed of sound is only sort of 0.2 kilometers per second or so. So this is basically Mach 10 motions, which are producing the line broadening in the CO line that they discovered. And these supersonic motions have been a long-standing problem. That is, what is the origin of these supersonic motions? And then secondly, and more importantly, how do they get damped out in order to enable star formation? Because with these very high velocities, the gas simply won't collapse on its own gravitationally, and you need some other mechanism by which you take that supersonic turbulence in these clouds and get it to remove some of the kinetic energy, which then enables collapse. Okay. This just makes a point that essentially all star formation occurs in molecular hydrogen. And before the discovery of CO, it used to be that people thought that stars would form in atomic hydrogen clouds. But essentially all star formation is well correlated with the molecular hydrogen or the CO line emission. So there are 3 different probes, which I mentioned before, for the molecular gas, which is contained in what are called giant molecular clouds, which are typically like the Orion cloud, which is shown here. So in Orion, this is actually a map of the dust emission. In Orion, there's a long cloud, which is roughly 50 parsecs in length, hence the name giant. And then that's in Orion A, and then Orion B, there's a second cloud, which has similar extent. And also, in both cases, there's an active H2 region, which is heating the gas, but in a very localized region. So here is the optical M42, and then Orion B is up there, both of which have OB star formation very plentifully. Okay, so I guess you're going to just have to bear with me hitting the wrong advance. So if you look at the giant molecular clouds, for some reason the bottom of this is cut off. The typical size is basically like the Orion cloud, and if 50 parsecs, 40 parsecs across, and containing roughly 300,000 solar masses of material. So they're extremely massive clouds, but not actively forming stars over the whole cloud. So if you look at nearby galaxies, this is M74. Oops. Maybe Andreas, having you come up all the time. Andreas, you're okay. So here are the summary of properties of the material in the giant molecular clouds. They contain 99% of the mass is in the gas, molecular hydrogen, and 1% is in the dust. And that's a good rule of thumb. And the dust is contained of either solid carbon or silicate. And typical dust grain size is 0.1 microns, 10 to the minus 5 centimeters. The number density of dust grains to gas is approximately 1 to 10 to the 11th. So that means if you were to get in an area of the interstellar medium where the gas density is, say, 1 hydrogen nucleus per cubic centimeter, you'd have to walk 1 million kilometers between the dust grains. Yet, amazingly enough, you look into the galactic plane and you do see this extended extinction, but it's not like you're actually looking into a GMC. You're looking at more diffuse molecular clouds. Okay, let's go to the next one. So, so the question is, how do you dissipate the turbulence or possibly magnetic support of the material in the clouds? And it's pretty clear that it's not simply gravitational collapse of these massive clouds, because if it was simple gravitational collapse, then the star formation rate would be much, much larger. The total molecular gas mass in the Milky Way is about 1 billion solar masses. And if they're collapsing on a certain cloud crossing time, the star formation rate, let's go to the next slide. The star formation rate would be, 10 times larger than it actually is. So the mechanism by which I believe that the turbulent motions are damped is by what is called orbit crowding in the spiral arms of the galaxy, where these represent the material motions of gas clouds separated by 250 million years between each X, and then the spiral arm potential is here in this simulation, and the the gas clouds come into the spiral arm from underneath and then exit out the top of the spiral arm. And when they're crossing the spiral arm, they can each cloud can collide with another cloud. And not all of them do, but that could also lead to star cluster formation, which one sees in the spiral arms. So the critical thing, though, is that the cloud collisions are infrequent. And if there's, let's see another slide. Yeah. Go back one, I guess. Let's see. Yeah. Okay, so the first sort of problem, which I've been thinking about for many years, is that the if you take the whole gas content of molecular hydrogen in the Milky Way and divide by the observed star formation rate, which is a few solar masses per year, you would expect that the lifetime would be only 2 gigayears. Yet, of course, the Milky Way is 10 gigayears old. So how is it that we still see active star formation in the Milky Way and residual gas? So the critical thing to recognize, in which everybody, myself included, working in the field, that kind of forgot about, is the fact that these clouds are filamentary. They're not spherical. Obviously, a spherical cloud can collapse to a single concentric center and produce a huge burst of star formation. But in the case of two filamentary clouds colliding, they may be at different angles, and so only a small part of the gas cloud is compressed as a result of ram pressure hitting the other cloud. And so the fact that the clouds are filamentary is critical to maintaining the star formation in galaxies. Okay, so what I want to do now is, because I've been kind of wordy and disorganized, is look at the overall evolution of this material as you go back in time. And this is a well-known plot from Maddow and Dickinson, which shows the growth in star formation rate density as you come from high redshift going to low redshift, and cosmic time is listed up above or down here. It's dramatically peaking at redshift 2, and also the activity, of course, in quasars increase to a peak at roughly redshift 2. So what is the reason for that? Is it due to there simply being more gas to accrete into massive black holes in the centers of galaxies? Or is it due to the fact that the gas is used more efficiently at, say, redshift 2 than otherwise? Okay. So to illustrate this, I want to, because the data which I'm going to show is actually measuring the gas content, not using CO, but rather using the dust material, looking at the Rayleigh jeans emission on the long wavelength tail of the dust emission. So just because a lot of you are not infrared astronomers, here's a simple model which I did with radiative equilibrium around a star cluster here, which I think in this case was, I've forgotten the luminosity that I put in, but in any case, the high energy photons in the UV are absorbed in the first boundary layer, and then those grains are heated to a couple hundred degrees. Then they emit at roughly 10 microns, and then that longer wavelength radiation goes out to a larger radius, and so on. And so there's a temperature gradient which decreases outwards. So the dust absorption coefficient, which is this one from Drain and Lee, which I use, it decreases as you go to longer wavelengths, of course. And here is 10 microns, 100 microns, and so on, as you go out to the radio. Okay, next. So here are three different models, three different models with masses ranging from in the dust cloud in the center from 10 to the 6 to 10 to the 7, 10 to the 8 solar masses. And if you look at the spectrum, of course, as you increase the mass of dust in the model, the dust becomes optically thick. Here's the original optically thin spectrum. And then when the short wavelengths become optically thick and absorbed, that these aren't seen from the outside of the dust cloud. And then on the other hand, when you go to the longer wavelengths out in the Rayleigh-Jeans portion of the spectrum, the flux increases linearly with the mass of dust in the model. So that's the facility which we use in this work in order to probe the mass at high redshift. You can't use ALMA to probe these very high redshifts in CO because the CO lines, once they're redshifted down to shorter wavelengths, to longer wavelengths, they move out of the ALMA bands. Okay. Thanks, Andreas. So here is an illustration of that calibration between the overall luminosity and the molecular gas mass as measured with CO 1 to 0. And in the case of this sample of 128 galaxies, because the ALMA basically doesn't have any, that's where the higher redshift Rayleigh-Jeans continuum is measured. So the high Z submillimeter galaxies, of which are 30 in the sample, they're measured all with the VLA. Whereas, the Z equals 2 galaxies can still be measured at ALMA, but using CO 2 to 1. So this average here is 5.6 times 10 to the 19 in these funny units. The Planck satellite, looking at the Milky Way, got an amazingly similar number of 6 times 10 to the 19 and versus 5.6 times 10 to the 19. So there's kind of basically a factor of 2 scatter in these points. So the calibration is really extremely good. But these are calibrations using the whole flux from the galaxy. You can't just measure a bright source in the center of the galaxy and expect them to hold up. Any questions so far? Yeah. Yes, at roughly above redshift 6. And it becomes a problem in the sense that the dust grains are also heated by CMB, which I've included in this model, but I didn't show it. The models curves that I showed were all for redshift 0, just so they're comparable. But at when you go beyond redshift 6 in CO, then there's a extreme problem that the CMB is also heating the CO, not just the star formation luminosity. And then also that the, well, I don't want to go into, yeah. Okay. So the logic of the analysis I'm about to show you, which shows the evolution of the galaxies, and this is really sort of the heart of the talk, is that I found in the cosmos field 700 galaxies which had detectable far infrared emission in order to get the starburst luminosity of the galaxies. And they also had the dust emission measured in the Rayleigh Jeans portion of the spectrum. So there are 700 galaxies in the range of redshift 0.5 to 5. So it's a substantial portion of the cosmic age. And then the question is does the star formation peak occur due to there being more gas in galaxies at that point, or is it due to efficiency in converting that gas into luminosity through either AGNs or star cluster formation? So the quantities which I'll point out are the star formation rates are from Herschel far infrared exclusively, no optical star formation rates, because I think they're not very reliable because they only see the first few magnitudes of visual extinction into the galaxy, but rather using entirely the flux from Herschel. So then the star formation efficiency is the star formation rate per unit gas. So it tells you whether, if the gas is being used up more readily, more efficiently than in local galaxies at redshift 0. And then basically these two quantities, the star formation efficiency and mass of gas, are compared as a function of cosmic age, stellar mass of the galaxy, and then whether the galaxy is above or below the main sequence line. And the biggest weakness of this analysis is, in fact, the lack of good definition of the main sequence beyond roughly redshift 2 or so. So there's a lot of room for improvement on this. Okay, so here is the overall gas mass is determined from the Rayleigh Jeans flux as a function of redshift for these 700 galaxies. And you can see that obviously, as you go out in redshift to younger galaxies, the flux in the Rayleigh Jeans increases dramatically, and meaning that the overall mass of gas is much, much greater. So for comparison, the Milky Way gas content is somewhere down here, roughly a factor of 10 or 20 less than these galaxies at high redshift. And so I'm going to take out all the individual points in the next plots and then show just the median and the, can you go back? The median and the average for these galaxies as a function of redshift. So next one. So here is the gas mass as a function of redshift using just the median points and the average. And then here is the star formation efficiency for the same sample as a function of redshift. And you can see that the star formation efficiency increases somewhat, but the overall mass is really the dominant thing, which is causing the increase. So if we look at the ISM mass as a function of stellar mass in the galaxy, determined from the Cosmos Float-C fitting, for which there is something like 700,000 objects in that catalog. Gas mass varies roughly as m star, the stellar mass, to the 2/3 power. And the star formation efficiency is independent of the stellar mass of the galaxy. So that's something very significant. It's telling you that the clouds at higher redshift are probably also self gravitating, because they only feel the potential of the material in the clouds, not the overall stellar mass of the galaxy center. And here's doing for the star formation rate relative to the main sequence at each redshift. And you can see that it's basically flat for the gas content versus the elevation above or below the main sequence line. And on the other hand, the star formation efficiency is significantly greater at higher redshift, increasing basically almost linearly. So I'm not aware of any other project which has been doing this kind of thing. And one of the things which I wanted to stress is that all of this was done with publicly available archive data. And it's, one doesn't have to do, good science. You don't have to go out and propose everything. There are huge archives for all these missions, which should be made better use of. Okay, next one. Yeah. Oh, that I don't know. I mean, that's just it's amazing that these points all hang together and move systematically. Yeah. Yeah. At least I'm happy. Audiences aren't always happy. Okay, so now this is kind of getting to the final summary. If you want to look and see how the evolution of the gas is occurring relative to the stars, this shows the gas content is derived from the Rayleigh-Jeans dust continuum divided by the gas baryons plus the stellar mass baryons. And you can see that the 50% line, where 50% of the overall baryonic mass is contained in gas, is occurring at roughly redshift 1.2, 1.3. And the next one. And so here's a summary of basic. Oh my God, I'm almost on time after all that stammering. So a quick summary is that, the gas dominates the stellar mass in galaxies, and we're all used to thinking of, the stellar constituting most of the baryonic mass of galaxies. And in fact, at high redshifts, as you might expect, at high redshifts, the overall gas content is, baryonic gas content is dominating. And so it's just a summary, which you can see later on. And in order to keep the gas content significant down to redshift 0, the filamentary nature of the GMCs is critical because when they collide and dissipate the turbulence, they're only doing it in a small part of the filament, which constitutes the GMC, not the whole GMC. And accretion rates get up to roughly 200 solar masses per year, which is pretty enormous. And I didn't show how the accretion is derived, but the way that it's derived is, in fact, to make the assumption that the galaxies evolve along successive main sequence lines as you come down in redshift, and on those intersection points with the main sequence, the gas content has to be equal to the mass which is observed in this study. So I think I'll stop at this point. Thank you, Andreas. What? You want this point? I got one question from Phil. Would have been good to get more questions from other. The troublemaker. We don't know. But what? No, I don't think so, because I mean that's a possibility, but they all have, there are aligned polarization of the dust grain and dust continuum, not for all these galaxies, but for a lot of galaxies. And that does tend to follow the filamentary structure, but you never know whether it's due to the fact that the motions in the gas are more significant than the strength of the magnetic fields. And so they drag the field along, or the field is controlling the gas morphology. I mean, the awful thing is about this field is that, everybody thinks that magnetic fields should be structurally important for these gas structures, but you can't measure the strength of the magnetic field, so you don't really know whether it's equivalent to 3 kilometers per second of turbulent flow in the gas.
Okay, should we?
Yeah.
Okay, so I want to basically continue where Nick stopped, but now we go a bit to higher redshifts. So what we have learned so far is that galaxies evolve very significantly over time, right? So they are very gas dominated, they're bursty, they are fed by those very strong 200 solar masses inflow. But the question is, how do galaxies get there, right? So how do they get there from their primordial formation? And that's what I want to focus on the next 18 minutes or so. And so really I want to show you some of the recent results that we have about the chemical and the structural transition of those very primordial galaxies formed here in the Epoch of Reionization to the cosmic noon. As Nick said, so ALMA is a very good instrument to do this, because basically provides the unique opportunity to study the rest frame far infrared light of high redshift galaxies, thanks to its very good efficiency in especially bands 7 and 6 and 8. And so from the dust continuum, what we can learn from that is about the dust masses, the ISM masses that Nick was showing before, and from the lines in the far infrared, we can learn about the kinematics of the warm gas, of the carbon, and also some other interesting results. And so as soon as obviously ALMA was online, people started looking at the highest redshift galaxy at that time. And specifically, the thing to target was the singly ionized carbon at 158 micrometers. which is a dominant cooling line. So it should be very visible in the high redshift galaxies that are very star forming. And indeed, so that was one of the first observations of a protocluster at redshift 5.3. And you see here this galaxy here, it's kind of it's a very starburst galaxies with a lot of infrared emission. So you see this nicely in the ALMA continuum image here on the right-hand side. But then you see other galaxies here too that belong to this protocluster. So it's a very interesting system. And when you look more closely, you see that those, I call them normal galaxies because they're not like crazy submillimeter galaxies. They emit this carbon 2 emission here. And from that, we then have focused on studying the kinematics as well, and of the warm gas, right? And also we have kind of confirmed or shown that C2 is a very good proxy for the dust obscured star formation, right? It's a log plot, yeah. Yes, yes. It's to first order. And that's the interesting thing, what causes the variations right there. And obviously it's yeah, it's not a one-to-one dependency. Yes, and this is not even at, so as soon as you go to lower metallicity systems, it gets even noisier, right? And it starts to break down at some point. So it works well for like metal-enriched systems. Yes. Yes. Yeah. 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 So, okay, so we have this one observation, right? And so the goal was then to expand this to larger samples, for which they can also obviously probe this relation here more. And so this is where the Alpine Turbine started. It was a 70-hour ALMA program, and in cycle 5, which I'm leading now. And the goal was to look at the single ionized carbon emission in 118 redshift 5 galaxies. And so this plot again shows this star formation, cosmic star formation density plot that Nick showed before, but now in equal steps of time. And so you really see at this redshift 4 to 6 range how the galaxies are really transformed in terms of their chemical and structural properties. And the other interesting thing here is that by construction, these are all main sequence galaxies. So they're kind of your typical galaxies at this cosmic time. It's like when you do a census of the population, right? You want to pick the kind of the typical representative galaxies. And these are basically the science goals. So the main point is obviously to measure the C+ emission, to measure the kinematics of this gas, measure gas fractions, outflows, and also the enrichment of carbon of the surrounding gas of those galaxies. And with the dust continuum, we can also study dust obscured star formation, which has never been done at this redshift before. And so, yeah, if you're interested in more, you can look at those papers, and also I have a nice review that you can look at. So the main point here is that it's really a multi-wavelength sample, right? So we have imaging here in the UV and also spectroscopy from Keck in the rest frame UV. And then in the optical, we have the Spitzer imaging. And then in the far infrared, we have this ALMA measurements. So we're kind of getting towards a very nice, comprehensive multi-wavelength view of those galaxies. And here, just to show, these are the 118 galaxies in carbon emission. You see the different structures. Some of them are mergers. Some of them are, very irregular. That's basically all the carbon gas around those galaxies. And so what were the main conclusion from Alpine? So we found very dust obscured system, like this one here. So that's a triple merger at redshift 4.7. And you see even in K-band, this VEST component is not visible, but it shows up very nicely in the C2 emission, which is shown in those white contours. And here's another example. That one's actually detected in the Spitzer imaging. which is the red optical light, but it's missing in the optical imaging. But again, it's visible in C2. And this kind of systems, they haven't really seen before statistically, right? And even at higher redshifts, and they have been now found with the Rebel survey, which is like Alpine, but at higher redshifts. So you see here, this is a galaxy at redshift 7.3. Here you see nice contours in white, the C2 emission. And then you see the companion at the same redshift here, which is not detected even if in the deepest Hubble imaging that we have, but it shows up in the C2. So that's very interesting. So there are very dusty systems out there at this early times. And then, as Nick said before, galaxies are gas rich. So we basically show this again at higher redshifts. So the point that Nick showed before are in blue, and then the high redshift points from Alpine are in red. There are multiple ways to measure the gas mass. And another way you can do is using the dynamical mass, which is an independent tracer, right? So the dynamical mass is basically everything. You subtract the stellar mass, you subtract the dust mass, and you get kind of a gas mass out of it. And it agrees very well. It's kind of a second test on Nick's measurements. So he did well. Another interesting thing is that with the C2 kinematics, we can look at the outflows of the galaxies. So how much gas is being pushed out by star formation or HN activity. And so what we did, we stack galaxies at low star formation rates. This is all redshift 5 at low star formation rates and at higher star formation rates. And we fit the C2 line and we look at the residual. And what you see here is that for the high star formation rate bin, we see those residuals at about plus minus 500 kilowatts per second, right? So that tells you that there's some outflow in those galaxies. And you can kind of constrain the mass loading factor, although with huge uncertainties. It's about 1. So the outflow rate is about comparable to the star formation rate of those galaxies. And then you can go further, you can compare this to simulation. And you see, for example, for the Eagle simulation, it kind of predicts a much, well, a factor of 2 more efficient outflow that we measure in the Alpine galaxies. It fits well with the local starburst, though. And finally, there are those very mysterious C2 halos that were found in those around those galaxies. And that basically tells you that you have the CGM gas that's already carbon enriched, and it has to get out there somehow through outflows. So you see here, this is the C2 halo size versus the UV or optical size. It's about factor 3 or so higher, larger, more extended. And it's still a bit a question what causes those C2 halos, right? You can have outflows, you can have satellite galaxies that are just hanging out there and enriching the CGM with metals, or you can just have heating from the C2 emission, as Sri was saying. It's very easily excited, right, and emitted. So there is a project I'm doing with a grad student here, Simon, to look at the fire simulations. And what we find there is that with the realistic feedback from the fire simulation, we can actually reproduce the C2 halos very well that are observed. So here the observations are in the dashed lines, and the fire predicted C2 halos and UV continuum sizes are in this range in blue and red. So that also hints towards that feedback is mostly and outflows are mostly responsible for these halos. And another cool thing is if you look at the star formation history of those simulated galaxies and you correlate it with the size of the C2 halos, is that they're kind of lagging behind. So when you have a starburst, you have a lot of outflows and you kind of push the gas out and you create those C2 halos. So that's a very nice work. And finally, this is more of it for the public, right? So we find we can with the C2 kinematics, we can search for rotators with respect to compared to the mergers in those samples, and we find about 15% of the 118 galaxies that we look at are they have a rotating structure, right? So they kind of settled into some kind of disk or a rotation dominated system. Okay, so this is all very nice, but one thing we are missing is the ionized gas, right? So we have looked with ALMA at the warm gas, C2 carbon, but what we're missing is ionized gas. And the ionized gas, you can measure from these rest frame optical lines here. So you can get the ionized gas kinematics, metals, the chemical enrichment of the galaxies, black hole growth, and recent star formation. That wasn't possible before. We have JWST, and now with JWST, that's possible. We can do this, and we can also, using the IFU capabilities of JWST, we can actually look at this resolved in a resolved way. And that's the follow-up. That's a very new program that I'm also leading. Follow-up of Alpine. It's the Alpine Crystal JWST survey. Weird name. And what it is, it's basically it's a subsample of the Alpine galaxies, so 18 Alpine galaxies, where we also have much higher resolution, spatial resolution, ALMA follow-up observations from the Large Crystal ALMA program and other programs. And then we obtained 60 hours of near-spec IFU data to really look at the optical properties of those galaxies. And then we also have JWST NearCam imaging in the rest frame optical from the Cosmos Web program. And just to advertise this a bit, because we were talking about Cosmos before, the Cosmos Web survey is the largest JWST program that has surveyed the continuous area of about 0.6 square degrees on the Cosmos field. So you see the Cosmos field is here, and the Cosmos Web program is right in the middle. We have those 5 filters, 4 NearCam imaging and 1 MIRI filter. And there's a ton of other programs that are targeting this area now, and we get a lot of more data. And so, yeah, as Phil was saying in introduction, this is all started basically with Nick. So thank you, Nick. If you want to know more about Cosmos Web, you can go to this web page. We have like a funny, like a Google map kind of interface where you can zoom in and look at the galaxies. It also made it to KTL morning show, but that was a fun experience. Anyway, so back to Alpine Crystal. So now we kind of we're filling in this diagram more and more, right? So we now have the JWST observations of these optical lines here. And very deep and high resolution JWST imaging. And again, we have ALMA here. And this is all at roughly matching resolution of like 0.1 arc seconds. So it's like a kiloparsec or 2 kiloparsec. Again, because it's a subsample, I don't want to be here too long. It's a subsample of Alpine. So again, main sequence, it's a bit more massive due to selection, obviously, because else we would have needed more than 60 hours of JWST time. Here's a stacked spectrum, just shows you all the beautiful optical lines, including some fainter auroral lines in oxygen. And we get this basically for every 0.1 arc second pixel for those Redshift 5 galaxies. And that's something very, very new. This hasn't been done before. So you see here all the 18 galaxies in the gradient is the H alpha map from the JWST IFU image spectroscopy. In cyan, you see the carbon 2 emission from ALMA, and in red dash, orange dashed, you see the dust continuum image by ALMA. And yeah, it's a very nice sample. There's a lot of things you can learn. For example, this one here is very interesting. So you have this dust cloud here that's kind of offset from the ionized ionized clouds gas here, image shown by H alpha, right? So there's like some kind of feedback that pushes the gas out and distributes it into the CGM of those galaxies. You can also look at kinematic maps here from the ionized gas. So these are H alpha kinematic maps. You can compare this to the ALMA kinematics maps from carbon to compare the ionized to the cold gas or warm gas. Just like very briefly what we learned so far, there's much more coming very soon because it's a very young survey. We find some low luminosity HEN, so actively accreting black holes in those galaxies. The black hole masses, they fall about on the local relation, which is not found by other JWST studies. And we find 7 out of 18 that have an AGN in there. We find this, this is one interesting case of another protocluster environment. And that's really cool. So the main sequence galaxy sits here in blue, and then you have this like funny green stuff. That's an O3 emitter. It's like a cloud that emits O3 light. And then you have here an AGN, and then you have a dusty star forming galaxy here. And then you have this outflow, and then you have this carbon plume here that's probably pushed out by some kind of feedback from this AGN. So there's a lot of stuff going on. Interesting, so what I'm showing here is the oxygen velocity dispersion. And so that's very high up here is where you have a lot of outflow feedback right here. So that's a very interesting system. And I think we also have Muse data that shows a gigantic Lyman alpha halo around the whole thing. And finally, we can look at the metal enrichment. So that's the metallicity versus stellar mass relation. So when you go to higher masses, you build up more metals, right? So you should be higher up. If you go to higher redshift, you would expect less metals because you have the 4 metals over time. What we find is that at redshift 5, those galaxies are pretty metal enriched, very similar to what we find at cosmic noon. You have about 600 million years or so to form your metals. And so when you look at the ejection rate of metals as a function of time for supernovae type 2 and HEV stars, you obviously see that as expected, you have mostly the supernova that contribute to the metal enrichment. We can also look at this resolved, and so that's a very nice work by Wu-Chi Wang, my postdoc, is looking at the CGM metal enrichment, and we find that it's equally metal enriched as the interstellar medium of those galaxies. So again, the metals have to be pushed out there to 10 kiloparsecs in distance. And if you look inside the galaxy, we find very flat metallicity gradients, and that also tells you that there's some efficient mixing of metals in the galaxies. So you don't see a metal gradient because usually you would find more metal-rich gas in the center versus metal-poor gas in the outskirts. And I think that's pretty much it what I have. I leave the summary up, but it's really a nice, it's a very interesting time because we have JWST, HST, and ALMA working at the same time. So we can really do these multi-wavelength studies at resolved scales. So we're going to learn a lot. And obviously, what we haven't done much yet is to compare it to simulations, because now we can actually do this a resolved comparison of simulations and observations. And that's all I had.
Thank you both so much. We started a few minutes late, so why don't we do a couple quick questions if there's something quick before we can carry our questions over to Wine and Tea.
Yeah, so that's a good question. So you can use the N2 emission in the far infrared, for example, which is a different ionization switches. So you can compare that to the C2, and they are, it's very expensive to get N2 with ALMA. I think that there's one study that has like 2 galaxies detected, and it shows that I think about 80% of the C2 gas is from the PDRs compared to the warm ISM, right? Yeah. But again, this is not at all resolved. That's just integrated over the whole galaxy. And, if you are shown here, you have to look at the spatial distribution of dust and gas cells here. Kind of mentioned. Yeah. Yes. Yeah. Yeah. Yeah, I mean, that's something we definitely want to do. Unfortunately, 18 galaxies is still not enough to do this statistically. We do see, so there's this example. We have another example where we do see higher velocity dispersion in O3 that kind of correlates with an AGN candidate. So there's definitely a lot of, I mean, at least in 2 cases, right, where we can see this effect. For the other AGN candidates that I mentioned here, they're really candidates, right? So we have medium resolution, near spectator only, but we see the H alpha broadening. But yeah, we have to go deeper to really look at those effects for the rest of the sample.